All right, there's one more type of video I'm going to make for class, and these are videos in which I solve a problem start to finish. And so you can have a chance to look at some of the techniques of the class. And let's take a look at this one. And this one concerns a rear window defroster. And you've seen these before. If you look at like the back window in your car, okay, there's a wire on it. And they take various forms, but we're imagining one that looks like this. And so there's a wire. And you pass a current through it. The wire acts like a resistor, dissipates energy, and then just warms up your window. This is the sort of thing, I'm 100% sure you're familiar with this. But let's talk about how this works. So first, let's go ahead and read the problem through. A rear window defroster consists of a long flat wire bonded to the inside surface of the window. When current passes through the wire, it heats up, melts ice and snow in the window. Okay. So for one window, the wire has a total length of 12.2 meters, a width of 1.8 millimeters, and a thickness of 0.11 millimeters. The wire is connected to the car's 12-volt battery and draws 7.5 amps. What is the resistivity of the wire material? And then what is the power dissipated? Okay, that's what we're asked. So the first thing, of course, we're going to do is we're going to strategize. And I'm going to treat this as a simple circuit problem. Okay, it's going to be a simple circuit. I'm going to have basically a power supply hooked up to a resistor, like so. That's my strategy. I've got a power supply with a potential difference delta V hooked up to resistance R, and then I have a current I that flows through the circuit. So it's basically our basic circuit. That's going to be our strategy. Solve the properties of the circuit. For my preparation, I'm going to draw some details. Okay, so let's go ahead and take a look. Let's make a diagram here. So the wire itself, okay, has a length of 12.2 meters. Okay, from end to end, and I put a potential difference across the end. So 12.2 meters, and I've connected it to a power supply between the two ends. But this blue wire is the thing I'm interested in, and it's got a length of 12.2 meters. And the cross section of the wire, it's a flat wire. Cross section looks like this. It's a flat wire, like so. The length of it, the width of it is 1.8 millimeters, or 0.0018 meters. The thickness, okay, from here is 0.11 millimeters. That is 0.00011 meters. That's the thickness. And I'm just going to cut to the chase here. The cross-section area is just the product of those two. Okay, it's just 0.0018 meters times 0.00011 meters. That's the cross-section area. And the length of it, we saw, was 12.2 meters. Okay? That's enough preparation, except I want to identify relevant relationships. That's another piece I want to do. Well, we know the current in a resistor is equal to delta V divided by R. And we know that the resistance is just equal to rho times L divided by A. Okay? And with that in hand, we're ready to solve. And the first step in the solution is going to be this. Okay, the wire is connected to the car's 12-volt battery and draws 7.5 amps. Well, I can calculate the resistance because our basic equation for our simple circuit was current was equal to delta V divided by R. I can rewrite it as resistance is equal to delta V divided by I. Well, if resistance is equal to delta V divided by I, I know delta V, the potential difference that's placed across the wire, is 12 volts. The current to the wire is 7.5 amps. And so as a consequence, I can solve for what the resistance is. And if I do that, I get a resistance of 1.6 ohms. Okay, so that's my first step in solution. And then I know that the resistance is equal to rho times L divided by A. And I'm pretty close to that because I computed the area here. It's just the product of those two things. I know that. And I also know the length of the wire. It's 12.2 meters. So I know the resistance. I know the length. I know the area. The only thing I don't know in that equation is the resistivity. So I can take those numbers, put them in the equation, solve for the resistivity. And if I do that, I get 2.6 times 10 to negative 8th ohm meters. And I want to assess that. That is a reasonable value for the resistivity of a wire. If we think back to our tables, that is not a wildly unreasonable number. And so that's going to be my assessment. My assessment is that number checks out. Next piece, of course, what we want to do is we want to figure out the power. Well, the power is going to be very straightforward because I'm given the potential difference and I'm given the current. And so the way we're going to calculate that is just going to say the power is equal to the current times the potential difference, 12 volts times 7.5 amps, and I get 90 watts. And here's my assessment. 90 watts is noticeable. It's kind of like comparable to the electric blanket problem we saw in class, was 82 watts. But it's not enough to like, you're not going to see your windshield glowing red or something like that. It's enough to warm it up. It's enough to defrost it, but it's not enough that it's going to get like scary warm and it turns off after a certain point. So my assessment is that number strikes me as being quite reasonable. And so that is how we're going to set up and solve this problem. So first piece of the puzzle, strategize, treat it like a simple circuit. Preparation, we gathered relevant variables, did a calculation of the area, did a solution, first of the resistance. With the resistance in hand, we could find the resistivity, and then finally calculating the power. And then we were sure to check ourselves that our resistivity that we calculated was a value that is comparable to what we might see for a wire. And the amount of power that we got was a number that was reasonable. If you got like 9,000 watts or 0.9 watts, that's not going to work. But 90 seems quite fine.